and anti-aromaticity. Remember that to be aromatic, you have to be cyclic, planar, fully conjugated, and have the correct number of electrons. Go ahead. You felt that the finale was too much, huh?
I'm not saying.
Oh, did I feel like it was too much? I enjoyed the bit with Cad Bane. Spoiler alert, right? Should I do anything? Oh, yeah. And I enjoyed the choice that was made by the small child that looks like Yoda. I thought that was good. I'm a softie, I guess, so I thought that was good. Yeah, I thought it wrapped things up nicely. I don't know that they need another season at this point, but I don't know. We could talk about it the whole time, actually, but let me diagram out my feelings about it for you. All right, so aromaticity, you got to have the right number of pi electrons, and the allowed number of electrons for this special stabilization is 2, 6, 10, 14, etc. This is just a series of allowed numbers of electrons, and if you were to try to define the numbers of that series without writing them all out, you would just say that it's 4n plus 2, where n is an integer greater than or equal to 0. N doesn't mean anything other than it defines the series of allowed electrons. We're going to learn today why that allowed number of electrons for special stability works. But before we do that, I just feel like it's important to emphasize how much you need to practice determining whether lone pairs on a heteroatom count as being part of aromaticity. So this is a related, I think we've done something like this before. This molecule happens to be called oxazole. One of the really sort of ways that organic chemists try to demonstrate their prowess is to know the names of cyclic aromatic rings that have heteroatoms in them. They're called heterocycles. And if you can bust out heterocycle names without like blinking, the O chemists in the audience will go, ooh. So another trick you may like to try out at parties, if you need a reference for good ways to talk about heterocycles, I can direct you towards a nice PDF, and you can work on words like oxazoladenone and just rattling those off. And it's benzotriazole, it works out pretty nicely. Happily married for 20 years based on she was actually not interested at all in the heterocycles. Anyway, how do we count these electrons? Well, you count all the electrons that are involved in conjugation. How do you tell which those are? Pi bonds. So 2, 4. Can the lone pair on this nitrogen count? The answer is no. You've learned why, okay? If you don't understand why, you need to fix that. Come talk to me. The basic idea is that this nitrogen's p orbital is already involved in this pi bond. Therefore, the lone pair cannot be in a p orbital. Therefore, the lone pair cannot be involved in conjugation or aromaticity. And then on the oxygen, a maximum of one of these lone pairs can be involved in conjugation and aromaticity for the same reason. If one of them is in a p orbital involved in conjugation with these other electrons, this one must therefore be in an sp2 orbital and not involved. Remember, to be part of conjugation, you have to be able to line up with the p orbitals in the ring. So we would say, yes, this is indeed aromatic. In contrast, if you were to draw, say, something like this with 2 oxygens, this gets kind of messy. How many pi electrons do we have? 2, 4, 6, 8. So this would be anti-aromatic, right? Your text points out that the base pairs, the bases in DNA and in RNA are aromatic. We won't worry about their structures of nucleic acids yet, and we'll return back to that a little bit later on in the class. Finally, we just want to emphasize that you can use aromaticity now. Go ahead.
How well are we supposed to be expected to predict if a cyclic structure is linear
How well are you supposed to be able to predict if a cyclic structure is planar? Yeah, so of the criteria, cyclic, what was it? Cyclic, fully conjugated, planar, and right number of pi electrons. Basically, if you have all of these three, that's sufficient, and it will be this way. It will be planar. If you don't, if you're anti-aromatic, sometimes the molecule will distort itself from planarity in order to avoid anti-aromaticity. So I can't really immediately think of an example where something would be aromatic, only it can't get planar. You could probably design a molecule to do that, but I can't think of one off the top of my head. The idea is if you're cyclic, fully conjugated, and have the right number of electrons, it's going to be favorable for you to be planar so that you can benefit from aromaticity. Okay, other questions? Yeah?
If it's not aromatic, does that instantly mean it's anti-aromatic?
If it's not aromatic, does that instantly mean it's anti-aromatic? No. This molecule here is simply not aromatic. Doesn't even have any conjugation. So there's three kinds of molecules: aromatic, anti-aromatic, and just plain old not aromatic. And the anti-aromatic molecules will be cyclic and fully conjugated, but they will have the wrong number of pi electrons. And that is 4, 8, 12, 16, etc. Multiples of 4, or 4n defines the series where n is greater than or equal to 0 and is an integer. Right, others? Yeah?
Are we supposed to, if it's anti-aromatic, that it's not planar?
Are you supposed to know that if it's anti-aromatic, it's not planar? No, I would say that just the idea is that anti-aromaticity is so destabilizing that sometimes, if they can, molecules will distort themselves to avoid being anti-aromatic. But no, I would just call this molecule anti-aromatic, because it would sort of be unfair to say, well, actually, because it's anti-aromatic, it should be not aromatic because it's going to change its geometry. No, you're just going to count the electrons to identify whether something's anti-aromatic. Okay, what else? Yeah? If you have an alkyne, would that affect its aromaticity? The alkyne situation is very much like the oxygen situation. Only one of the two pi bonds can participate. So, of course, you'd have to draw, oh boy, I'm making stuff up now. 2, 4, 6, 8, 10, 12, 14, 2, 4, 6, 8, 10, 12, 14. Yeah, you could, I don't know if this molecule exists, but you would say it's aromatic, and you would only count one of the two pi bonds because only one of the two pi bonds can overlap with the other p orbitals.
Wait, that is aromatic with 14 electrons?
This would have, 14 electrons is on the list.
Oh.
So yes, aromatic. Now, I don't know if this molecule exists. Gasp.
Nobel Prize?
Gasp. No, worse, terrible. Sorry, I don't know what came over me. I need to redraw this because it didn't go particularly well. Sorry. And now I'm having to count. This is why you don't make stuff up on the fly. 1, 2, 3, 4, 5. That would be 10 electrons, and that is an allowed number. 2, 4, 6, 8, 10. Is that?
Yeah.
Yes? I can't count. I can't do arithmetic. There. That has 10 pi electrons. So if it exists, it would be aromatic. The thing I drew before wasn't actually fully conjugated. Watch out for that. Yeah.
Under what circumstance would we, like, how could we have an aromatic compound with only 2 pi electrons?
How could you have an aromatic compound with only 2 pi electrons? I'm so glad you asked. You could have a cyclopropane ring with a double bond here and a positive charge there. And that would have resonance structures in which the positive charge could be here or there. So there's 3 atoms in a conjugated array, 3 p orbitals are on this ring and only 2 electrons in them. While we're thinking that our rings look like stuff, I don't know whether you guys think that this is like the little green men from Toy Story or something, but who's in charge here? The claw. Looks a little happier than the sad robot ring. Others? Did I miss another hand? Okay. Yeah, go ahead.
Are there any, like, I guess you sorted through it earlier, but where it has the right amount of pi bonds, but like, it's not obvious that it's not conjugated?
Can you think of an example where it has the right number of pi electrons, but for whatever reason it's not fully conjugated? Sure. So here is sad robot molecule with 2 antennae, and it's not fully conjugated. So even though it has the right number of pi electrons to be aromatic, it's just plain old not aromatic. Yeah. Okay. And speaking of sad robot molecule, we can start to use aromaticity as a way to explain, just as we've used resonance before as an explanation for why some compounds are more acidic than others or why some reactions are faster than others. I think I mentioned last time, and then I forgot to look up the pKa's. One of these is more acidic than the other. To see which one is more acidic, you simply draw the conjugate base. So let's remove one of those protons here. Let me just highlight which ones we're talking about. Which proton is more acidic? Well, you draw the conjugate base, except now my 7-membered ring is struggling. And you put the negative charge here, and then you do the same for the 5-membered ring. And both of them are cyclic and fully conjugated. Up here we have 8 electrons in the pi system. Here we have only 6 electrons in the pi system. So this would qualify as anti-aromatic, and then the one on the bottom would qualify as aromatic. So based on that and the stability of the conjugate base, which of these 2 protons is more acidic, pink proton or orange proton? Orange, right? And we could look up the pKa's. I'm sorry I didn't. They are known. But this anion, cyclopentadienyl anion, is actually quite stable. It's not a regular carbanion. It functions, you can use it as a ligand for metals in inorganic chemistry and catalysis, so it's quite stable. In contrast, we could think about a different but related question, and that would be to take the same rings but think about a different pattern of reactivity. So here we're going to ask which reacts fastest in an SN1 reaction. To make that assessment, we will simply draw what the carbocation intermediate would be, because that's forming that carbocation is the rate determining step of the SN1 reaction. Looks a little happier. I don't know. So let's draw the carbocation. In both cases, you have a positive charge that's stabilized by resonance. Which of these carbocations is more stable? Slightly less sad robot on top, right? Why is it more stable? because it's aromatic. It has the correct number, 6 electrons in the pi system, whereas this has only 4 and is therefore anti-aromatic. Right. Okay, so be able to use that as an explanation, be able to recognize anti-aromatic compounds. What's this thing here? This is, I forget what it's called, but it's a molecular box. And this was made by Professor Donald Cram, and he won the Nobel Prize in the 80s, shared the Nobel Prize with 2 other scientists for developing molecules that bind other molecules. So this is a box, and Professor Cram's lab made this and then put inside it a molecule that was a precursor to cyclobutadiene. Remember, I told you this was normally so unstable that you can only observe it at 4 Kelvin in a matrix of solid argon. So that's like not something that most of us will ever have the chance to observe. But they put a precursor to cyclobutadiene inside this cavity. There's a hole in the middle of this molecule, right? That another molecule can fit in. And this precursor, they generated cyclobutadiene by irradiating it with the right wavelength of light, and then it stayed there indefinitely at room temperature because it was held inside this box where it couldn't react with anything else, which is kind of crazy that something that could not even be observed at room temperature could sit on the shelf, just sitting there being cyclobutadiene and sitting there and staring at you. So if you want to come look at this afterwards, it's kind of fun. One of the fun parts about chemistry is sort of like Legos or Tinker Toys, just building new structures. You got to be careful though, because if all you're doing is building new structures, that becomes what we call gee whizology, which is sort of like, oh, look at that cool thing that you made, but it doesn't do anything, and therefore who cares? All right. So now let's talk about where this rule about the number of pi electrons comes from. And I'm going to try not to make this too technical, but I do want to talk enough about the orbitals involved that you can see where this comes from. So recall that if you have a alkene, you make the pi bond of the alkene by bringing together, and let's just imagine that we're looking, just for simplicity's sake, I'll draw the alkene from the side, but then afterwards we're going to view it from above, all right? So the pi bond in the alkene is associated with this pi molecular orbital. The different colors represent different signs of the wave function. The electrons that are in this pi orbital simultaneously occupy both areas above and below the nucleus, above and below the plane of the molecule. And conceptually, we will often draw this pi orbital just to remind ourselves where it comes from. We will draw the pi orbital as sort of 2 p orbitals on adjacent atoms next to each other with the same wave function sign. But got to understand that when we draw this, we really mean this. Okay? Is that all right? MO theory says that when you mix 2 atomic orbitals together to get a new pi orbital, so we're mixing 2 of these 2p orbitals and we're getting a new pi molecular orbital, you must also do the minus combination, and that gives you the pi star, which is the antibonding orbital. Which is what you get if conceptually if you draw 2 p orbitals adjacent to each other, but they have opposite wave function sign. Opposite wave function sign means that actually in between the 2 nuclei there is no there would be no electron density. This is an antibonding orbital, and we will call it the pi star. All right? Does that sort of look vaguely-ish familiar? Okay. So, and for our purposes now, what we're going to do is to view the molecule from above. So we'll do the Newman projection with our evil Sith eyes, and we will look down at the molecule. And basically, I'm going to draw, let's put the Sith eyes over here. By the way, Obi-Wan Kenobi coming out on the 25th of May. That's going to be pretty cool. Yeah. I'm always depressed when The Mandalorian ends because then it's a whole year before another season, and who can stand that? But it's okay. I just watch it again multiple times. So we'll draw the pi orbital looking down from above like this. 2 p orbital lobes on adjacent atoms, and then below the plane you have the lobes that are of opposite wave function sign. Now, conjugated systems, what we can do is instead of mixing 2 p orbitals together to get 2 new pi molecular orbitals, we're going to mix 4 p orbitals together to get 4 new pi molecular orbitals. So you probably saw this when you did butadiene in the Diels-Alder reaction. You mix 4 p orbitals on adjacent atoms together, and the lowest energy one is this one that would be delocalized over the whole molecule. We could sort of draw it like this, but you'd remember that this is above the plane of the pi bonds, and then below you'd have another sort of lobe in the back. Okay, we still looking familiar? Okay. And recall that there were many of these. There were 4 of them because we mixed 4 2p orbitals together, so we have to get 4 new pi molecular orbitals out. And I don't know how much you went through this, but again, looking down from above, you can envision these orbitals as 4 p orbitals on adjacent atoms, and then you fill in the various wave function signs. So in the lowest energy one, you have all same sign of the wave function. In the next highest one, you have 2 the same and then 2 the opposite, with a node in the middle where electron density would go to 0. The next one, and I'm not going to expect you to generate these from scratch. There are ways to think about it and do it, but that's beyond the scope of what we want to do here. This is just the results of MO theory calculations. But you can sort of see a pattern that emerges that with each orbital that we go up in energy, we have an increasing number of nodes. The more nodes we have, the more high in energy the orbital is. And once you know how the relative energy levels of these orbitals, you can start filling up the available orbitals, with the available number of pi electrons. In this case, we have 4 electrons in the pi system. And so what that means is 2 here, 2 here, and this is HOMO, and this is LUMO. Still good-ish? Okay. And the stabilization we get from conjugation, if you sort of look at this pi 2 orbital, it looks like it should be about the same as 2 pi bonds adjacent to each other, only that's 1 pair of electrons that's sort of delocalized. The stabilization you get from conjugation has to do with the fact that you have a pair of electrons that are delocalized over 4 nuclei, and it's all in phase and there are no nodes. This orbital is lower in energy than a pi, an isolated pi bond. Another way to think about these orbitals in terms of their energies is to look at the number of times that you have same sign of same sign of the wave function between individual atoms. When you're on adjacent atoms and the orbital that spans those 2 atoms has the same wave function sign, we're going to call that a bonding type situation. It's not a separate bond, we'll call it a bonding interaction. Each of these is a bonding interaction in the lowest energy orbital. So you have 3 bonding interactions here. In the next orbital, you have 2 bonding interactions, but you have 1 anti-bonding interaction because you have a place in between the 2 atoms where the wave function sign goes to 0. And so overall, we have a net 1 bonding interaction. And similarly here, we have 1 anti-bonding interaction. And then up on top, we have 3 anti-bonding interactions. This is another way of counting the nodes, but it gives you a sense for stability, because the more bonding interactions you have, the more stable something should be. All right? I lost anybody yet? Yes, it's okay. Questions? All right. Don't panic. I'm never going to ask you to generate the pi molecular orbitals for a conjugated system. I might show them to you and ask you which one's HOMO versus LUMO. That's a matter of being able to count the nodes, rank them in energy, and then fill them up with the available electrons. So basically, if you can count, you could solve a problem like that. In this class, I tell people, what math are you going to need in organic chemistry? If you can count, you probably got 95% of it, then there may be just a little bit of subtraction. And other than that, oh, you have to be able to divide by 2. That's also useful. But other than that, no math. All right, so let's now compare a conjugated triene with benzene. Because the situation here is that we have 3 pi bonds in conjugation in both cases, but one is aromatic and the other isn't. One experiences extra stability, the other doesn't, and the question is why. So let me just say that if, in a similar way as we made 4 pi molecular orbitals above, if you have 6 atoms involved in conjugation, you're going to be combining 6 p orbitals, p atomic orbitals, together to get 6 pi molecular orbitals out. Don't worry about where these come from. Don't worry about the math. If it doesn't make sense, just accept what I'm going to draw as the outcome of the math. And I'm only going to draw the 3 lowest ones because those are going to be the only ones that matter for us. So the lowest energy one, as you might expect, has same wave function sign on all 6 atoms. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. The one following that would have the same wave function sign on 3 of them, and then opposite wave function sign on the other 3. There's 1 node here, so we've got, if we're counting nodes to help us order them in energy, 0 nodes, 1 node. In pi 3, you've got 2 nodes, and that's what that would look like. And we could go up and do the others, but that's not going to be necessary because right now we're only worrying about where the electrons are. We have 6 electrons in the pi system, so we fill them up, and this is the highest energy orbital. And this highest energy orbital is about the level of energy you would expect for an isolated pi bond, but now you have 2 sets of electrons in lower energy orbitals, and this is the more stabilization that you get because of conjugation. Notice that this lowest energy orbital, if we count the number of times that atoms are adjacent to each other with the same wave function sign, we get 5 bonding interactions. So, bonding interactions. 5 here, we would have 1, 2, 3, 4 there, minus 1 anti-bonding interaction, so that it would be 3 here. And then here we'd have 1, 2, 3 bonding interactions minus 2 anti-bonding interactions, 1 there. Okay? And that just sort of reflects how many times the wave function stays the same as we go from atom to atom. Now, let's look at benzene. And conceptually, we're going to make the orbitals from benzene by taking atoms 1 and 6 and just putting them next to each other. All right? So let's see what would happen. So let's take this lowest energy one, and instead of having them out in a line, we'll put them in a ring. 3, 4, 5, 6. Okay? And actually, we can do this for let's do this for the pi 2 orbital as well. Let's just make a ring. 2, 3, 4, 5, 6. Okay? Now, let's count the number of bonding interactions we have in, we're going to call this orbital pi 1 as well. We'll call this one pi 2. How many bonding interactions do we have here? 2, 3, 4, 5, 6. By making it a ring, we get a bonus bonding interaction. 6 bonding interactions instead of 5. So this is one of the reasons why benzene is so much more stable. Yeah.
For the one above that, is it actually just one bonding interaction, or is it just 2 and 2?
I'm sorry, where? Here?
Yeah.
1, 2, 3, 4. And then you minus 1 because of the antibonding interaction in between these two. Yeah, you offset bonding and antibonding. Yeah. Okay. What else? Yeah. Is there one less bonding interaction in the pi 2 orbital? Let's see. 1, 2, 3, 4. Yeah. That's interesting. Let's see. 1, 2, 3, 4, but minus 2. So there's only 2 net bonding interactions here. Okay. Now, it turns out that converting this one into a cyclic system doesn't work out conceptually. There's some symmetry rules you have to follow. So I'm just going to show you the results of the third pi orbital, and you'll have to accept them on faith. They're going to look sort of weird. In the third pi orbital, you have electron density on 2 of the atoms, and then over here. But unlike the second pi orbital, where the node is in between atoms, the node in the pi 3 orbital actually coincides with 2 of the atoms. And just as you pointed out, we've got 1, 2, 3, 4 bonding interactions versus 2 anti-bonding interactions. Here, in this other orbital, we only have 2 bonding interactions. Because there's a node that coincides with these middle atoms, we don't count that as an interaction at all. We only count adjacent atoms. All right? So if you are ordering if you are ranking orbitals in energy by counting nodes and or bonding interactions, one of the things you would conclude is that pi 2 and pi 3, whereas they were different in energy here, they share the same number of nodes here and the same number of bonding interactions, and therefore they are equal in energy. Okay? And in terms of what we get, it's almost as though we took these two, we had 1 bonding interaction and 3, and we sort of averaged them. But the picture that emerges, if we were to draw these an energy diagram of these orbitals and where they show up, you have this lowest energy one, which is pi 1, and then you have pi 2 and pi 3 that are different in shape but equal in energy. Another mathematical term that we will use occasionally for describing things that are equal in energy is degenerate. That does not mean of low moral quality, it just means equal in energy, all right? So now let's look at what happens, and we could go on and show you where the antibonding orbitals come from, but it turns out they follow a similar pattern. These are the empty antibonding orbitals, and these are the bonding ones. If we fill these orbitals up with the available electrons in benzene, what you find is that you have 2 in the lowest energy one, and then you have pairs of 2 electrons in these degenerate orbitals. There are 4 here. Okay, so this is where the 2 comes from in the 4n plus 2 rule, and this is where the 4n comes from. Because you can expand this out to other molecules. For example, dare I do this? Well, sure, why not? 10-membered ring? If you had another aromatic system like this, this would be a 10-membered ring aromatic system with 10 pi electrons. I don't know if I can draw a 10-membered ring, frankly, so we're just going to say a 10-membered ring with 10 pi electrons. We would fill these, and these. This would be the dividing line between empty antibonding orbitals, and this would be bonding orbitals. And you would see that we have 1 low-energy pair of electrons, and then degenerate groups of 4 electrons at each increasing energy level. So this is where the 4n comes from, because depending on the allowed numbers of electrons that allow you to fill all of the bonding orbitals and none of the antibonding orbitals. First include you need 2, and then thereafter you need multiples of 4 so that you can completely fill the equal in energy bonding orbitals. Okay, that I think was a bit of a whirlwind and a little crazy, and maybe you don't care, and that's fine. If you just want to memorize the 4n plus 2 rule, that's good, but it's sometimes nice to know where it comes from. The idea is that when you make a ring cyclic, it changes the number of bonding interactions. One of the orbitals goes down further in energy, and then the other 2, the pi 3 and pi 2 that were in this linear molecule, come down to be equal in energy. So thereafter you have 1 that's lowest, and then pairs of orbitals afterwards that are equal in energy. And the way you fill them completely without filling any antibonding orbitals is you have to have 2 plus a multiple of 4. Okay, questions you want to ask about that? Yeah?
Just looking at a molecule, would you be able to tell which is the lowest pi orbital and which of the other 2 are higher energy?
Looking at a molecule, would you be able to tell which is the lowest energy one versus the others? Yes, the lowest energy one is always the one where the orbital is on all of the atoms but without changing wave function sign. Others? Yeah?
So in the case of the benzene ring, would that mean there's 2 homos and 2 lumos?
That's right. For the benzene ring, what is the HOMO, what is the LUMO? Well, you have 2 of the two highest occupied molecular orbitals. So, yeah, there we go. And 2 lowest unoccupied molecular orbitals. Yeah. What else? Yeah.
Can you show us what this looks like for an anti-aromatic compound?
Great. So what about an anti-aromatic compound? So before I do that, I should say that it turns out there's a lovely mnemonic device that works in a pretty well quantitative way, even though you do no molecular orbital calculations. And the idea is you take for your aromatic molecule, say for benzene, you draw a polygon that's a perfect hexagon, and you inscribe it within a circle, And every time the polygon touches the circle or at the vertices, you put an orbital energy level. Right? That gives you the pattern that you get from the MO calculations. One that's lowest and then pairs all the way up. So without knowing anything about MO theory, you can predict, and if you do this, this is not a very nice circle or a polygon, but if you do this precisely, the difference in distance actually on your page between these two orbitals, these two lines, is proportional to the difference in energy between the orbitals. It's like kind of good it works out that way. But yes, you can do this for anti-aromatic compounds as well. So let's take a circle. I wonder if, that was nice. You see that? I drew the circle and I held it down and then it drew me a circle. So let's just do that again. Ooh. Now I wonder if I can, hey, come on. All right. I wonder if I can do a square now. That's fantastic. New things Notability can do. That's awesome. So now I have no excuse for ever drawing a bad shape again. For cyclobutadiene, which looks like this, you take the polygon that represents that ring, a square, you inscribe it in a circle, and wherever the corners of the square hit the circle, you've got orbitals. Now you can start to see where this anti-aromaticity comes from. For one thing, in the benzene ring and in other aromatic compounds, when you fill the orbitals with the available electrons, they're all lower than this dividing line between antibonding orbitals and bonding orbitals, right? But if you apply that same reasoning, if you apply that same reasoning here in the case of cyclobutadiene, the two orbitals that are higher than the lowest one are actually on the boundary between anti-bonding and bonding orbitals. In fact, we would call them non-bonding. So by being aromatic or by being planar and cyclic and fully conjugated, it's like some of your electrons are like they weren't even in a bond at all. So you go backwards instead of forwards. You lose the benefit of bonding. And if we count here, we have 4 electrons in the pi system. Let's put 2 here. What are we going to do here? What's the rule from general chemistry that you do when you have equal in energy orbitals and you need to fill them? One at a time and parallel in spin, and then it's the, what is that? I forget what principle that's called. Hund's rule. That actually comes from quantum mechanics. It's like amazing. My mind blew up when I started teaching the advanced OChem class and learned where that comes from. But we won't talk about it here. But in any case, whoa, now you have a molecule that has 2 electrons, but not only are they at this higher energy non-bonding orbital as though they weren't involved in a bond at all, but they are also unpaired. And you've learned, did you do a chapter on radicals? I think you did radicals in 351, maybe. Unpaired electrons have unique reactivity, and especially a diradical would be a problem. So anti-aromatic compounds, the problem is twofold. You have unpaired electrons, and they are at a non-bonding level, so it's like they weren't even in a bond at all. You drew cyclobutadiene as though there were 2 pi bonds, but actually what you've got is 1 pi bond and 2 unpaired electrons. And so what this molecule will do to prevent this from happening is it will distort its shape. Distorting its shape breaks the degeneracy between these 2 higher energy orbitals, and it's going to move, I'm going to erase the shapes. If we distort the shape, what that will do for us is it breaks the degeneracy and it moves one lower in energy and the other higher in energy, and then we can not have unpaired electrons. Okay? All right, questions you want to ask about that? So if you want to have some fun drawing shapes, you can go back and look at the cyclopentadienyl anion, draw the polygon, inscribe it in a circle, and demonstrate to yourself that it's aromatic, that it fills all of the bonding orbitals and none of the anti-bonding orbitals. Similarly, do the same thing for cycloheptatrienyl anion and convince yourself that this is anti-aromatic because it has 2 electrons split apart in a degenerate high-energy orbital. So this is a useful mnemonic device to help you out with aromaticity. Go ahead.
Would it be with the point down or the point up?
Right. So when you draw this diagram, it's always point down because you got to have the lowest energy one at the bottom. Yeah. So you inscribe the polygon point down. Okay. What else? Yes.
What about the cyclopropene?
Cyclopropene, same thing. I'm glad you asked. I get to draw another circle. Ding. That sort of looks equilateral. Anyway, yes, you would draw it like this, this, and this. In cyclopropene, you'd have 1 lowest energy orbital and then 2 higher energy antibonding orbitals. If you have 2 electrons in it, it would be aromatic. Now you could ask me, what if you fill all of those at the top? Would it still be aromatic? Yes. However, that would be, let's see, with only 2 electrons, cyclopropene has a positive charge. So if we added 4 additional electrons, that would be 3 minus. And what we would be saying there is, yes, it's aromatic, and it is more stable than your typical trianion, but it's not very stable. Yeah. Okay. I think that's probably enough. We could go on and do chemistry, but I know how you feel about the last 2 minutes of class, and it's Friday, so see you next week.